the binomial probability formula. So we're going to be looking at a binomial distribution. So first, well, I guess, so in a binomial distribution, in a Bernoulli distribution, well, having a Bernoulli random variable. In that situation, we're looking at circumstances that have only two outcomes, such as acceptable, defective, head, tail, up, down, right, wrong, true, false, survive, dead, success, failure. So in these situations, we're going to be looking at situations where we have these two possible outcomes. We'll be looking at, well, what is the mean, what's the variance, what's the standard deviation, what does the distribution look like? And so, let me give you some notation. So let S denote success, F denote failure, and these are the two possible outcomes. Let P denote the probability of success, and Q the probability of failure. So the probability of success is P, the probability of failure is Q. Let N denote the fixed number of trials. Let X denote the specific number of successes in trials. So it'll be, well, 0, 1, 2, 3, da, 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 all the way out to N. It could be any of the values, 0, 1, 2, 3, da, 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 all the way out to N. Let P denote the probability of success in one of these N trials. Let Q denote the probability of failure in any one of these N trials. Let P of X denote the probability of getting exactly X successes during the, amongst these 10 trials. So note the following sort of confusion that you may have, that X and P both refer to success. So P is the probability of success in any particular trial. X counts the number of successes in an experiment consisting of N trials. Let me describe a Bernoulli process. And then I guess I'll tell you a Bernoulli random variable, a Bernoulli distribution. So in a Bernoulli process, the outcome of a trial results in the dichotomous classification of events. Each trial must have all their outcomes classified into two mutually disjoint categories, which we will call success and failure. The trials must be independent so that the outcome of any individual trial does not affect the outcome of any of the other trials. The probabilities remain constant for each of the trials. So the probability of success in any one trial is P, and the probability of failure in any one trial is Q. A Bernoulli process consists of these Bernoulli trials. A Bernoulli random variable, X, counts the number of successes in a Bernoulli process. A binomial experiment. So in a binomial experiment, Well, we're going to have a Bernoulli process that has a fixed finite number of trials. So, in a binomial experiment, the procedure has a fixed finite number of trials, n. The outcome for each trial results in a dichotomous classification of events. Each trial must have the outcomes classified into two mutually disjoint categories called success and failure. The trials must be independent. The outcome of any trial does not affect the outcome of the other trials. The probabilities must remain constant for each trial. The probability of success for any trial is P. The probability of failure for any trial is Q. So that we have that P plus Q is equal to 1, or that Q is equal to 1 minus P. So a Bernoulli process that has a fixed finite number of trials is called a binomial experiment. A binomial random variable counts the number of successes in a binomial experiment. We will denote the fact that X is a binomial random variable by stating that X is equal to P n comma P. So let me give you the binomial probability formula. So the binomial probability formula says that the probability of having X successes well, let's say the probability of having R successes is NCR P to the R times Q to the N minus R. I can write it as a binomial coefficient, or in the NCR notation, or I can write it in the factorial definition, n factorial over R factorial n minus R factorial. Or I can write Q is 1 minus P. I can write it, well, as a binomial coefficient in the NCR notation or in the factorial notation. So it's likely that you'll see the binomial formula written in any of these 2, 4, 6 different ways. I'll probably mostly use this, the NCR, P to the R, Q to the N minus R. I'll probably use that mostly. So let me give you a rationale for why this formula holds. So suppose you have n trials. N trials. So you could have, well, some successes. So you can have some successes and some failures. So in this case, well, you're going to have R successes, because I want to figure out the probability X is R. So you have R successes. And the rest, failures. And so you have R successes. And well, you have a total of n trials. And so the rest of them is just n minus R. So you have n minus R failures. And so you have R successes and n minus R failures. So you'll have some successes with probability P, some failures, some successes, some failures, some successes, some failures, etc. I don't care. You can either, I don't know if it starts with a success or a failure, but whatever. And so your R of them are going to be successes. So you're going to have P to the R. So if you multiply these out, well, I'll try. So if you multiply this out, well, it doesn't really matter that the order. So I just count how many successes there are. Well, I know there are successes. That's P to the R. And I count how many failures there are. Well, there's N minus R. Okay. But, you know, for each of these sorts of situations, okay, but it could be that, well, maybe the first one isn't a success, maybe it's a failure, etc. You know, so the question is, well, how many different ways can you write this? Well, how many different ways can you have R successes? And so it's done in N choose R different ways. So, and the R number of successes. Done in N choose R different ways. Therefore, the probability, so thus, the probability of having, oops, oh, someone just asked, when do we have our next test? So we have our next test when we are done with chapter 6, which is probably right after spring break, which is April 10th or something, somewhere around that. I believe like something around, so not quite a month from now, like in 3 weeks, I believe. So I think it'll be in 3 weeks. We have to finish off chapter 6. So we're in chapter 5. So when we're done with chapter 6, yeah, so we'll be done with chapter 6 mostly next week, right? So it'll be, I believe, in 3 weeks. Yeah, whatever that is. So, yeah, I think like April 10th or something. Okay, so, so thus the probability I don't have that. There it is, okay. So thus the probability of having R successes out of N trials is just, well, oh, maybe I should call that Q. Is, well, P to the R, Q to the R, right? P to the R, Q to the N minus R, times, well, how many different ways I can do that, which is NCR. Well, maybe I should write that as NCR. So that's the number of different ways I can do it. So I have R successes, I have N minus R failures, and I can do this number of successes in NCR differing ways. Therefore, that's the probability of having R successes. Okay. Okay, so when an adult is randomly selected, there is a 0.85 probability that this person knows what Twitter is. Suppose we want to find the probability that exactly 3 of 5 randomly selected adults know of Twitter. Does this procedure result in a binomial distribution? Well, let's see. I have to have a fixed finite number of independent trials. Well, I have here 5, so that is a fixed finite number of trials. They're randomly selected, so they're independent. So yes, there are 5 trials which are independent. Next, does each outcome result in, well, does each trial have 2 possible outcomes? Well, either you know of Twitter or you don't. So each trial has 2 outcomes. Is there a constant probability of success? So in this case, success. So do we have success? Yes. Success is that they know of Twitter. Is there a fixed probability of success? Yes. So there's a constant probability of success, 0.85, that the adult knows of Twitter. Therefore, yes, this is a binomial experiment. Differing ways of finding binomial probabilities is to use the binomial probability formula, to use some sort of technology. So here, N is the number of trials. X counts the number of successes among the N trials. In this case, you want R, you want X to equal R, you want R successes. P is a probability of success in any one trial. Q is a probability of failure in any one trial. You could also use some technology such as the TI-84. You would use binom PDF. If you're finding the probability X is equal to R, you would put in N, then P, then R. If you want to find the probability X is less than or equal to R, you would use the binom CDF, N, P, R. In Excel, you would use, to find the probability X is equal to R, binom.dist, R, N, P, false. If you're doing the probability X is less than or equal to R, then it's the same command except you say true for cumulative at the end. In Mathematica, to find the probability X equals R, you would use PDF, binomial distribution, in P, in P, and then R. For the probability X is less than or equal to R, you'd use CDF, binomial distribution, N, P, R. For R, you would use, well, the probability X is equal to R, you use D, binom, R, size equal N, prob equal P. For the probability X is less than or equal to R, use P binom, R, size is n, probability is x. And for the, for stat tests, you would use the binomial distribution, and you plug in success and number of trials. Okay, yeah. Or you could also use a table. So there are tables that are available that you can use. Oh, good. So with n equal 12 and p equals 0.8. So n is 12, here's 12. P equal 0.8, so p is 0.8. Let's look at 4, 5, and 6. So for 4, 0.001, 5, 0.003, 6, 0.016, and 7, 0.053. There are additional techniques that we will discuss future, like the next chapter. Oh, and so, which can be used to approximate values of some of these discrete probability distributions, such as the binomial distribution. So, strategies for finding probabilities. If n is, if your calculation involves less than 5 numbers that you have to calculate, then you should use the binomial probability formula. Otherwise, if n and p are such that they are in one of the tables, then you should use the table if they're exactly in there. Note that you won't get as accurate an answer because there's some rounding that is done. If those conditions, if you're not able to look in the table and if there are too many calculations to do, then you can use an approximation if the approximations are applicable. There'll be some conditions. Obviously, we haven't looked at them yet. And you have to check if those conditions hold up. Otherwise, then you would use some sort of technology. So, let's do the following. Given there is a 0.85 probability that a given adult knows Twitter, use the probability formula to find the probability of getting exactly 3 adults who know of Twitter when 5 adults are randomly selected. So in this case, n is 5. The number of trials is 5. It's a fixed finite number. They're independent. We want to find the probability of getting exactly 3. Well, success is that the adult knows of Twitter. So that is success. We have the probability of success is 0.85. Therefore, if I have an 85% chance of success, I have a 15% chance of failure. So Q is 0.15. So let me determine the probability. So the probability that X is 3, using the probability formula, is 5C3, which is 10, times 0.85 cubed. I have a 3 here. Times, probability of failure. Again, if I have 85% chance of success, I have a 15% chance of failure. All to the power of 5 minus 3, which is 2. 0.15 squared is 0.0225. 0.85 cubed is 0.614125. Multiply those together, so you get 0.13817813. A coin is tossed 16 times. Find the probability of getting exactly 14 heads. So we have a fixed finite number of trials, 16. They're, of course, independent. The fact that you get head, tail on one particular trial does not affect the fact that you get head, tail on another trial. I'm assuming that this is a fair die. So I'm assuming, well, so success in this case is head. You're counting heads. So success is head. The probability of success is 1 out of 2. I'm assuming a fair coin. I want to find the probability of getting exactly 14 successes, 14 heads. So let's use the binomial probability formula. So 16C14, 120. 1/2 to the 14, 1 over 16, 384. 1/2 squared, 1/4. So you get 15 over 8192, 0.001831055. You could look this up in a table. So n is 16. 16. And p is 0.5, and you want to find the probability of having 14 successes. 0.002. So the probability of having 14 successes is 0.002. Notice it's the same, but of course we've rounded. So you get, well, only the rounded to 3 decimal places when you're looking in this particular table. So let's do okay, let's go to the TI-84. Okay, so let's do the TI-84 here. So the way that we're going to be doing this is going to be very similar for how we're going to do this for the next dozen probability distributions that we look at. Click on second. Go to VARs, and right above it says distribution. So this is what we're looking for. Here we want to find the binomial distribution. So there are lots of them that we're going to be using. We'll go from the bottom, actually. So now there is a binomial PDF and a CDF. PDF if I have an equal sign, CDF if I have inequality. I have a equality, so I use P. Number of trials, 16. Number of successes, 1/2, 45. How many successes do I want? 14. 0.0018310547. Let's use Excel. Where's Excel? Okay, here wait 1 second. Okay, so now let's do Excel. Okay, so Excel. So let's try to find the probability of having 14 successes. Let's make this bigger. Okay, so I want 14 successes. Oops. So binomial distribution. I have 16 trials, each with a probability of 1/2. Oh, wait. Number of successes. I have 14 successes. Number of trials, 16. Probability of success is 1/2. And I do not want, I want to be able to type it. I do not want this to be cumulative. So that's false. 0.0018311. Next is to Mathematica. Where the heck is Mathematica? Oh, I know. Okay. So let's do Mathematica. So we want this to be equal. There's not an inequality. So do PDF of the binomial distribution. And the parameters are 16 trials and the probability of 1/2. Successes. Probability of success is 1/2. And we want exactly 14 successes. And so I get 15 over 8192. Oh, what the heck? Okay, so that was a horrible typo. I did that. Okay, so 15 over 8192, or numerically 0.00183.105 468.750. Okay. Now let me do this in R. So D binomial 14 successes. And the number of trials is 16, and the probability is 1/2. 0.001831055. Here. Oh wait, that one doesn't. Wait, one's. There's that one, okay. Must be this guy. Where the heck? Okay, no. Let's try this one. No. I must. Oh, it's right there. Okay, the third one. There it is right there. Okay, so let's go to binomial distribution. So for StatDisk Online, so click on binomial distribution. So probability analysis, probability distribution, and binomial distribution. There it is. So we have 16 trials. Probability of success was 0.5. And let's actually just do 14. And so 0.0018311. Okay, good. Let me go back. Oh, I should show that there. So actually, I did show this, how to do it on StatDisk. Okay. Let's go back. Do you have anything there? Okay. Let's go back. Okay, so if a coin is tossed 10 times, find the probability of getting at least one head. So I have a fixed finite number of trials, 10. Success, head. Probability of success, assuming, well, we have a fair coin, is 1/2. Therefore, this is a, and each of them are independent. So I have a binomial experiment. This will be a binomial random variable. I'm counting the number of successes. I want to find the probability of getting at least one head. So it's a probability of getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 heads when I flip a coin. So the probability of getting one head is, well, there are 10 trials, so it's 10C1. 1/2 to the 1, because you want one success. 1/2 to the, well, 9 failures. 1/2 to 9. Plus, well, we have 2 successes, so 10C2 times 1/2 to the power 2, because you have 2 successes. 1/2 to the 8, because we have, well, 8 failures. So we have 3 successes, 7 failures, 4 successes, 6 failures, 5 successes, 5 failures, 6 successes, 4 failures, 7 successes, 3 failures, 8 successes, 2 failures, 9 successes, 1 failure, 10 successes, no failures. So you add these up, you calculate each of these, add them all up. It's a lot of work. What is easier? Well, finding the complementary event in this particular case is much easier. So rather than add up all these, let's do 1 minus the probability x is, well, less than 1. That's a complementary event. Well, how many numbers are less than 1? How many whole numbers are less than 1? Well, only 0. So the complement of at least 1 is none. So I want to do 1 minus the probability that none of the times you get ahead. You keep flipping a coin and you just never get ahead. It's just always tail. So 1 minus 10C0, you have no successes. 1/2 to the 0, you have no successes. 1/2 to the 10, because you have all of them are failures. 10C1, 10C0 is 1. 1/2 to the 0 is 1. 1/2 to the 10 is 1/1024. 1024 minus 1 is 1023. And so we have 1023 over 1024. 0.999023438. So that's a probability of getting at least one head. Okay, so let's see if I have, probably do have. So I can look up in my table. So if I look in here, it's 10. There are 10 successes. So I have here 10 successes. N is 10. And P is 0.01. I'm sorry, the probability of success is 0.5. I want to find the probability of having at least one. So I'd add up all these to get my answer. Or, well, since I know that the total area under this is 1, I can, instead of adding up from 1 and above, I can just say, well, let's do 1 minus this amount. And so the probability x is greater than or equal to 1 is 1 minus 0.001, so 0.999. Very similar to what we got here. Let's use the TI-83. So let's do the complementary event. So I'm going to have to take 1 minus the complementary event. This is the binomial. Doesn't really matter in this case if I do PDF or CDF, because they'll both give me the same answer, and just in this one case. Number of trials is 10. Still flipping coins, it's 1 out of 2. Success. I don't want any successes. 0.999,023,4375. Let me do Excel. And so I want to find the probability of having at least one success. So let's get rid of the complementary event. Now unfortunately, we can't directly use the cumulative, because cumulative is everything to the left. It's a left tail, and we're doing a right tail. So we have to use a complementary event, no matter what. So binomial distribution. Number of successes. I don't want any successes. Number of trials, 10. The probability. You want it to be cumulative? Don't care. Either true or false will give you the same answer, because it's 0, so it doesn't really matter. 0.9990234. Let's use Mathematica. Okay, so let's do Mathematica. So, okay, well, be lazy and just cap it there. So 1 minus PDF. Binomial distribution, 10 successes. 1/2 is the probability of success, and I don't want any successes. Okay. So I get, 1,023 over 1,024. Just like we had from before. Or if you want to do it numerically, 0.999,023,43,75,00. Let's do R. Oops, sorry. So let's do the complementary event. So 1 minus binomial. I don't want any successes. And the size is 10. And the probability of success is 0.5. 0.9990234. And let me do this. Okay, so third one, so 10.5. Okay, so binomial distribution. I have 10 successes. Probability of success is still 0.5, and I want at least 1. Okay, so I have here 10 successes. Probability of success is 0.5, and I want x to be greater than or equal to 1. So 0.9990234. Okay, good. So I have here, if I have the inequality less than, then the complement of less than is greater than or equal to. The opposite of less than or equal to is greater than. The opposite of greater than is less than or equal to. The opposite of greater than or equal to is less than. The opposite of not equal is equal. So this tells you how to look at how to rewrite these equalities, inequalities in, well, as a complementary event. So let me do the following. If, on average, 1 ship in every 10 is sunk, find the chance that out of 5 ships expected, at least 4 will arrive safely. So let's see if this is a binomial random variable. So there are a fixed finite number of trials. There are 5 of them. And in this case, it's 5. They're independent. The fact that 1 ship is sunk does not affect the fact that another ship sinks. Success in this case is, well, that the ship will arrive safely. I can either say, notice that one of them says the ship is sunk, the other that the ship arrives safely. It's probably easiest to formulate this where I'm saying that success is that the ship arrives safely. So success is that the ship arrives safely. Therefore, the probability of success is, well, since 1 ship in every 10 is sunk, then 9 ships out of every 10 arrive safely. So the probability of success is 0.9. I want to find the probability, what is the chance, that at least 4. So at least 4 is greater than or equal to 4. In this case, doing it directly is much easier than the complementary event. Greater than or equal to 4 just says, well, I want to find the probability of that either 4 or 5 of these arrive safely. And so let's do that. So I have 5 trials and I have 4 successes. So 5C4, probability of success is 0.9, all to the power 4. If I have a 90% chance of success, I have a 10% chance of failure. And 5 minus 4 is 1. Plus, well, the probability of having 5 successes. So 5C5. Probability of success is 0.9. I want to have 5 successes, so to the power 5. Probability of failure is 0.1, and I want no successes. I want no failures, so to the power 0. 5C4 is 5, 0.9 to the 4, 0.6561. 0.1 to the 1 is 0.1. 5C5 is 1. 0.1 to 0 is 1. 0.9 to the 5 is 0.59049. So if you add these up, you get 0.91854. Let's look this up in my table. So n in this case is 5, p is 0.9. I want to find the probability of getting at least 4 successes. So I will add up these 2 numbers here. The point, well, whatever, the point 328 and the 0.590. So you get 918. So if you add these up, you get 0.918. Okay, so you could also do okay, so since I have this picture here, I want to find the probability x is greater than or equal to 4. If I use technology, and all of my technologies, I'll always be looking at, for any inequality, a cumulative. And so the command that you get, well, except for that's right. The command that you always are looking at is something involving less than or equal to. So I want to reformulate this as a complementary event. So rather than greater than or equal to 4, I'm going to look at taking away everything less than or equal to 3. So let's look at 1 minus the sum x is less than, the probability x is less than or equal to 3. And so if I do my TI 84, I'll have to do 1 minus the binomial distribution. And this will have to be CDF. How many trials? There are 10 trials. The probability, oh, wait, no, there are 5 trials, 5 trials. Sorry, there are 5 trials. The probability of success is 90%. And we want at least 4, so I get rid of the first 3. So I want to get rid of the first, for everything less than or equal to 3. That will give me the remaining 4 and above. 0.91854. Okay, so let's do that. Let's do Excel. I want to figure the probability that X is greater than or equal to 4. So again, I'm going to have to do the complementary event. And so 1 minus binomial. Oh, where's the equal sign? One minus binomial distribution of number of successes. I want to get rid of the first 3 successes. Number of trials is 5. Probability of success was 0.9. And I want this to be cumulative. 0.91854. Let's do Mathematica. So 1 minus CDF of your binomial distribution. With parameters, what, 5 and success is 0.9. And I want to get rid of the first 3 successes. 0.91854. Let me do R. So again, the complementary event, so 1 minus P binomial. Get rid of the first 3. This number of trials is 5, and their probability is 0.9. And so I get 0.91854. Okay, so let's do this. So this is 5. So the size is 5. Success is 0.9. And you want 4 or above. And so do that. And you want 4 or above, so here it is, 0.91854. Okay, good. Let's do the following example. A die is rolled 5 times. Find the probability of getting 3 exactly 2 times. And so, n in this case is 5. You have a fixed finite number of trials. Success in this case is getting a 3. Well, rolling a 3. So, if you look on a die, you can either roll a 1, a 2, a 3, a 4, a 5, or 6. Therefore, the probability of just rolling a 3 is 1 out of 6. And again, the fact that you roll a 3 doesn't influence the next time that you roll your die. So these are independent trials with a fixed finite number of success, fixed probability of success. Probability of success, success in this case is again rolling a 3. So the probability of success is 1 out of 6. I want to find the probability of getting exactly 2 successes out of the 5 in the 5 trials. So 5C2, probability of success is 1 out of 6, and I want 2 of them. If I have a probability of 1 out of 6 as a success, then the probability of failure is 5 out of 6. If I have 2 successes, then the other 3 are failures. 5C2 is 10. 1 over 6 squared is 1 over 36. 5 cubed is 125, and 6 cubed is 216. And so you get 0.16075,10288. Let me go on the TI-84. So, oops. On the TI-84, I'll do binomial distribution. And this will be exactly 2 successes. You want to roll a 3 twice, yeah. So you roll it 5 times with a probability of success is 1 out of 6, and you want to roll it 3 twice. 0.16075,10288. Okay, so let's do Excel. I want to roll the 3 twice. So binomial. Number of successes is 2. Number of trials is 5. Number of probabilities 1 out of 6. And I do not want it to be cumulative. So you get 0.16071. Let's do Mathematica. So PDF binomial, so I want a PDF is equal binomial distribution. There are 5 successes, 5 trials. Probability of success is 1 out of 6 of only a 3. And you want to do that exactly twice. So you get 625 out of 3,888. 0.16075,1028807. Let's do R. So, exact. The binomial size is 5. The probability of success is 1 out of 6. 0.16071,0751. So for five successes, okay, so there, it's 160, and you want exactly how many? 3, 2. You want 2. You want to roll a 3 twice. 0.1607510. Okay. Good. Oh. So the binomial distribution is such that, well, the expected value of a binomial random variable is NP. The variance of a binomial random variable is NPQ. The standard deviation of a binomial random variable is radical NPQ. So let's recall some facts. First, let me write the binomial theorem, and let me write it in the same way that I wrote it when I proved it. So the way that we use it in statistics rather than in mathematics. So P plus Q to the power n minus 1 is the sum R equaling 0 to n minus 1 of n minus 1 CR, P to the R, Q to the n minus 1 minus R. Let me note that differences are translation invariant. So subtraction is translation invariant. So n minus 1 minus x minus 1, the same as n minus 1. Let me distribute the minus sign inside the parentheses. So minus x plus 1. The ones cancel, so you get n minus x. So this says that n minus x is equal to n minus 1 minus the quantity x minus 1. Let's recall some properties of Pascal's triangle. So the absorption property, that n times ncx is equal to that x times ncx is equal to n times n minus 1 cx minus 1 for x between 1 and n. So let's try to show the following. That if x is a binomial random variable, then the expected value of a binomial random variable is just n times p. So the expected value of a discrete probability distribution, by definition, is the sum of x p of x. Well, I know that x here goes from 0 to n. So it's the sum x equals 0 to n for binomial random variable. The probability formula for x successes is ncx p to the x q to the n minus x. So when x is 0, 0 times anything is 0. So I can go from 1 to n rather than starting at 0. By this property, the absorption property of Pascal's triangle, x times ncx is n times n minus 1 cx minus 1. So let's replace x ncx by n minus 1 cx minus 1. Let me bring an n, which is constant, outside the summation, and one of the p's outside the summation, which is also a constant. So this is equal to np times the sum, x equals 1 to n, of n minus 1 cx minus 1, p to the, well, I brought out one of the p's, so it's p to the x minus 1, times q to the, well, n minus x, by its algebraic fact, is the same as n minus 1 minus x minus 1. So I'm going to replace this n minus x by n minus 1 minus x minus 1. Now, let r equal x minus 1. So wherever I see an x minus 1, I replace x minus 1 by r, replace x minus 1 by r, replace x minus 1 by r. When x is 1, 1 minus 1 is 0, r is 0. When x is n minus r is n minus 1. And so, writing this in NCR notation, I have that this is equal to np, the sum r equaling 0 to n minus 1, n minus 1 cr, p to the r, q to the n minus 1 minus r. But by Pascal's triangle, by the binomial theorem, this is just p plus q to the n minus 1. And so, oh, why did I make these all red? And so this is equal to p plus q to the n minus 1. And so, p plus q is 1. 1 to any exponent is 1. And so I have np times 1 is np. And that's what I wanted to show. Next, let me write the binomial theorem in the form p plus q to the n minus 2 is equal to the sum r equaling 0 to n minus 2 of n minus 2 cr, p to the r, q to the n minus 2 minus r. Let me also note, again, that differences are translation invariant. So n minus 2 minus r minus x minus 2 is, well, the 2's cancel, so you get n minus x. So n minus x is equal to n minus 2 minus the x minus 2. Also, x times x minus 1, multiply x inside the parentheses, is just x squared minus x. Therefore, x squared is equal to x times x minus 1 plus x. Let me also write down the next of those absorption properties. If you remember, I wrote down 2 of them in a row because I said, well, these are the specific ones that absorption properties that you're going to be using. And so, x times x minus 1 times ncx is equal to n times n minus 1 times n minus 2 cx minus 2. So, if x is a binomial random variable, then the variance of x is equal to npq. So, let's try to prove this. The variance of x is equal to the expected value of x squared minus expected value of x quantity squared. And so, the expected value of x, we've already shown that that's mu, that's equal to n times p. So we just showed that right here. So I'll just replace the expected value of x by np. Next, well, by the binomial probability formula, this is just equal to n cx times p to the x, q to the n minus x. And now let me use the this formula here, this algebraic formula. Okay, so if I use this algebraic formula, the fact that x squared is equal to x times x minus 1 plus x, then let me distribute the ncx, p to the x, q to the n minus x inside the parentheses. So this is equal to the sum, x equals 0 to n of x times x minus 1 ncx, p to the x, q to the n minus x, plus the sum, x equaling 0 to n of x ncx, p to the x, q to the n minus x. But this is just the expected value of a binomial random variable, which we know is equal to np. When x is 0, 0 times anything is 0. When x is 1, 1 minus 1 is 0 times anything is 0. So instead of going from 0 to n, I'll go from 2 to n. By the absorption property, x times x minus 1 in Cx is n times n minus 1 n minus 2 Cx minus 2. That's just the absorption property. Let me bring n minus 2, and a p squared outside the summation. So what remains is, well, the n minus 2 Cx minus 2. I've taken out 2 of the p's, so that's a p to the x minus 2. And then what remains is q to the n minus x, and these other 2 terms. Let's just bring down these last 2 terms and replace n minus x by n minus 2 minus x minus 2. So I'm just going to replace n minus x by n minus 2 minus x minus 2. Wherever I see an x minus 2, I'm going to replace x minus 2 by r. I'm going to replace this x minus 2 by r, this x minus 2 by r, this x minus 2 by r. When r is 2, when x is 2, r is 0. When x is n, r is n minus x. But this is, by the binomial theorem, p plus q to the n minus 2. And so by the binomial theorem, this is just p plus q to the n minus 2. P plus q is 1. 1 to the unit power is just 1. Let's bring down each of these from before. And let's multiply the p squared inside the parentheses. So I get an n squared p squared minus np. The n squares, p squares cancel. So I just get np minus np squared. Factor out np. You get np times 1 minus p. But 1 minus p is q, and that's what you wanted to show. So we're done. McDonald's has a 95% recognition rate. A special focus group consists of 12 random selected adults. For such a group, find the mean and standard deviation. Use the range rule of thumb to find the minimum and the maximum usual number of people would recognize McDonald's. So in this case, n is 12. I have a fixed finite number of independent trials. Success is that they recognize McDonald's, and the probability of success is 0.95. So I want to find the usual number of usual minimum and maximum numbers, which is mu plus or minus 2 sigma. So I've got to figure out mu and sigma. Well, by the above formula, the first theorem that we just proved, we have that mu is equal to n times p. 12 times 0.95 is 11.4. We have that sigma equals radical npq. The square root of 12 times 0.95 times, well, if you have a 95% chance of success, you have a 5% chance of failure, so 0.05. And so you get 0.7549834435. So now, let's find the minimum usual number. And so mu, 11.4, minus 2 times sigma, 0.7549834435. So you get 9.890009331129. Let's find the maximum number, the maximum usual number. So mu, 11.4 plus 2 times sigma, 0.7549834435. So you get 12.9099668871. Okay, so actually it's 11.
Is symmetric if p is 0.5. So if I look here, Find table I here. So if you look at 0.5, notice that it's symmetric. Notice that if you go here down, same as going here, same numbers. So we have that if P is 0.5, the distribution is symmetric. Whereas it's skewed to the left if P is greater than 0.5, and it's skewed to the right if P is less than 0.5. So the binomial distribution is symmetric if P is equal to 0.5. It is positively skewed when P is less than 0.5. It's negatively skewed when P is greater than 0.5. The larger n becomes, the less pronounced the skewness of this binomial distribution. So for large n, the distribution, the binomial distribution, will look somewhat symmetric. If both NP and NQ are greater than or equal to 5, then the binomial distribution is approximately symmetric. As n keeps getting larger and larger, the binomial distribution tends to look like a symmetric bell-shaped distribution, what we'll call a normal distribution. We've shown that for a binomial distribution, the expected value, the mean, mu, is NP, whereas the variance is NPQ. Since Q is always less than or equal to 1, then the variance is always less than or equal to the mean for a binomial distribution. So let's look at some examples here. So let's just look at the shape of your distribution. Well, the shape of a binomial distribution, and see how it changes as we change P, and actually also how it'll change as we change N. So determine the shape of the following binomial distribution with the following parameters. N equals 7, P equals 4.5. Since P equals 0.5, then my distribution is symmetric. Next, let's try to determine the shape of the following binomial distribution where N is 8 and P is 0.3. Since 0.3 is less than 0.5, then my distribution, my binomial distribution, is positively skewed. Next, let's try to determine the shape of the binomial distribution where N is 500 and P is 0.5. Well, since P is 0.3 and 0.3 is less than 0.5, then our binomial distribution will be positively skewed. But since N times P is 150 and N times Q is 350, then they're both greater than or equal to 5. Therefore, my distribution, my binomial distribution, is actually approximately symmetric. So if you looked at the graph of your binomial distribution, by eyesight, it would look symmetric. If you really look closely, really close, you can see, oh, actually, it's slightly positively skewed. But to your eyes, to looking at it, visually, it will look very, very close to being symmetric. It would be very difficult for you to see visually that it's not symmetric. So even though it is positively skewed, it's very minor, is really almost perfectly symmetric with a very minor amount of positive skewness. Next, determine the mean, standard deviation, and variance for the binomial distribution with the following parameters. N equals 80, P equals 0.8. So let's find the mean. Well, by the theorem that we just proved a few minutes ago, the mean, the expected value of a binomial random variable is NP. So 80 times 0.8, 64. Therefore, the mean with these parameters is 64. Let's find the variance. So again, by the theorem that we just proved a few minutes ago, the variance for a binomial random variable is just NPQ. 80 times 0.8 times 0.2. If you have a 80% chance of success, you have a 20% chance of failure. So Q is 0.2. And so if you multiply these together, you get 12.8. Let's determine the standard deviation. So let's take the square root of the variance, the square root of 12.8, 3.5777,08764. It is claimed that a particular flu shot is effective 60% of the time. If the flu shot is given to 20 persons, how many are expected to benefit from the shot? So this is a binomial experiment. I have a fixed finite number of trials, 20. I have a fixed probability of success. Success is that the flu shot is effective. So the probability of success, P, is 0.6. I want to determine the expected number that will benefit from this shot, the expected number of successes. So expected number is NP. 20 times 0.6 is 12. And so, well, if I had asked a third grader how to do this problem, they also would have gotten the same answer. If you say it's claimed that a shot is effective 60% of the time, is given to 20 persons, how many do you expect to benefit? Well, 60% of 20 is 12. So yes, it's what we think it should have been. Next, in a binomial distribution consisting of 5 independent trials, probabilities of 1 and 2 successes are 0.4096 and 0.2048 respectively. Find the parameter P of the distribution. Also find the standard deviation of the distribution. So we're given as a binomial distribution. And we're given that n is 5. Next, Q is 1 minus P because it's a binomial distribution. And the probability of R successes is NCR, P to the R, Q to the N minus R. So we are given that the probability of 1 success is 0.4096. Well, by the binomial formula, I have 5 trials. I want to choose one of them to be a success. The probability of success, I don't know what it is, but I call it P. And so there are 1 success, and there are 4 failures. Again, I don't know the probability of failure. I'll call it Q. 5C1 is 5. And so we have that 5P to the, 5P times Q to the 4th is 0.4096. We're also given the following fact. Now, the probability of 2 successes is 0.2048. So out of the 5 trials, there are 2 successes. And so probability of success is 2, and the probability of success is P. There are 2 successes. The probability of failure is Q. And well, the other 3 are failures. 5C2 is 10. Therefore, 10 P squared Q to the power 3 is equal to 0.2048. .4096 divided by 0.2048 is 2. So write this as 2 over 1. I can divide both P, Q, both 5. I can divide 5 by 5 to get 1. Divide P by P to get 1. Divide Q to the 4th by Q to the 3rd to get Q. Divide 10 by 5 to get 2. Divide P squared by P to get P. And divide Q to the 3rd by Q to the 3rd to get just 1. So I have that Q over 2P is 2. Multiply both sides of my equation by 2P. So 4P is Q. Let's rewrite Q as 1 minus P. So 4P is 1 minus P. Add P to both sides of my equation. And so 5P is equal to 1. Divide both sides of my equation by 5. So P is equal to 1/5, 0.2. And that's what we wanted to determine. We wanted to determine P. So P is 0.2. Now, I also want to determine the standard deviation. So the standard deviation for a binomial distribution is radical NPQ. So N is 5, P is 0.2, Q is 0.8. So I want to find the square root of 0.8. 0.894421, no, I'm sorry, 0.894427191. Okay. Next, let me show you an alternative way of proving the fact that the expected value of a binomial random variable is NP, and the variance of a binomial random variable is NPQ. So let's do that. So this will be, well, a little bit more sophisticated of a way of showing this, but it's less computationally intensive. So it's really not using the facts that you know from junior high and high school. It's expanding on those. But it turns out that now that we have enough background, you should be able to appreciate this. It'll be much easier. So let X be a binomial random variable with N trials and P probability of success. Oh, that's a horrible typo. There. For each of the N trials, that's supposed to be an N. As a typo says end, it's supposed to be N, just N. For each of the N trials, we have, I must have been using voice or whatever to type this in rather than typing it in myself. So that looks like a typo from you know, not knowing exactly what I was saying. So, for each trial, we have the following. We have the sample space S, this fancy S here. It'll stand for the sample space. It'll consist of two outcomes. S for success, F for failure. And well, we will have a random variable X. This random variable X will equal 1 if we have a success, and 0 if we have failure. So X will take on two values, 0 and 1, depending on if I have success or failure. The probability that X is 1 will be denoted by little p. Note that that says the probability of success is p. The probability that X is 0 is q. Note that means the probability of failure, since X is 0 when we have failure. So the probability of failure will be q. So let's try to prove the following: that if X is a binomial random variable, then the expected value of X is NP. So we're going to be using a whole bunch of the facts that we derived back in section 5.1 to do this. So let X be your random variable, the output for one of your particular random variables for one of your trials. So for each trial, the expected value of X is the sum of X, P of X. Well, in this case, there's only two outcomes that can occur: 0 or a success or failure. And so the outcome for a success or failure are either 0 or 1. So 0 times the probability of 0, which is Q, plus 1 times the probability of 1, which is P. 0 plus P is P. So for each trial, the expected value is P. So now, suppose you have n trials. Then, the fact that they're independent in this case doesn't make any difference. So suppose you have n trials, then the expected value of X is the sum of the expected value of the sum of all these X's, all these outputs of this random variable for each of these n trials. So it's the sum of the expected value for each of these random variables, the outputs of each of these random variables. Well, the expected value for each of them is P. So the sum I equaling 1 to n of P is just NP. You're adding P plus P plus P plus P. Adding those n times, you just get NP. And so I've shown that the expected value of your random variable is just n times P. And you're done. So as you notice, it's less computationally intensive. But you have to know things. You have to know that the expected value is a linear function that you can, that these are equal. Next. And, it didn't take that long for us to show it, but back in section 5.1, earlier. Sorry. Oh, boy. Sorry about that. So it didn't take it that long to do it earlier this morning, but we need to use those facts. We needed to use those facts. Next. Oh boy. Sorry about that. Okay. Next. The variance of a binomial random variable is equal to NPQ. So we want to show that again. So sorry about that. Okay, so sorry about it. In the previous theorem, we showed that the expected value of X is P for every for each trial. So let's calculate the expected value of X squared. Well, by definition, S is the sum of X squared times P of X squared. Let's plug in 0 and 1. Those are the only two possible values of my random variable X. And so let's plug in 0. So 0 squared times probability of 0 squared plus 1 squared times probability of 1 squared. And so 0 squared times p times q times plus 1 squared times p. Oh, sorry. Okay. Sorry about that. Okay, so zero. Come on, stop. Oh boy, I don't know why. Okay, so 0 squared times q is 0. 1 squared times p is p. And so I get expected value of x squared is p. Therefore, the variance is the expected value of x squared, p, minus expected value of x, which is p squared. Factor out of p. So there's p times 1 minus p, but 1 minus p is q. So for each for each trial, the expected the variance of x is pq. Now, sorry. Okay, I might have to get something to drink. Sorry. I'm gonna take a minute off. I'm gonna get something to drink so I can continue. So 1 minute break. Okay. Okay, yeah, that's much better. Okay, sorry about that. Now it's much better. So we're trying to find that the variance
of a binomial random variable was NPQ. So from the previous theorem, we'd shown that for each trial, the expected value of x was p squared. We calculated that the expected value of x squared was also p. Therefore, using this simplifying computational formula for the variance of x is the expected value of x squared, p, minus expected value of x, p squared. We factor out a p to get p times q. Since each of our n trials are independent, then the variance of x, the variance of the sum I between 1 to n of x of I for each of your trials is, by what we proved earlier this morning, if actually we only proved it for 2. Actually, we only did prove it for 2. If there are, you can prove it also for n of these by using, I have to do that next time, I forgot. So if you also just use mathematical induction, it's easy to see that the variance of the sum of n independent random variables is the sum of their variances. But the variance for each trial is PQ. Since these are a constant, I'm adding up PQ plus PQ plus PQ n times. And so it's just n PQ. And that's what I wanted to show. So again, it's a simpler computation than what we did back, well, previously. So this is an alternative proof. These 2 proofs are the alternative proofs of what we proved earlier today about the fact that the expected value of a binomial random variable is NP, and the variance of a binomial random variable is NPQ. So that finishes off section